Okay, well, good morning, everyone, and thanks to the organizers for inviting me. I also want to thank Patrick for making a good choice with his, wardrobe this morning, and also for setting a nice stage for me because he alluded to a few things. Well, one thing in particular that I want to talk about today, and that is the role of effective heat capacity in Arctic amplification. And so, what Patrick alluded to was some early work by Minabe and others who talked about the role of effective heat capacity in understanding the seasonal cycle of Arctic warming. And so, as he alluded to, the idea is basically in the summertime, when you melt sea ice and you have more open ocean, the effective heat capacity of the Arctic is higher, and so that helps to explain why you have a minimum in Arctic warming and therefore a minimum in Arctic amplification in the summertime. And so, others have subsequently written, papers on that. Lily Hahn has a more recent paper on that. And so what I'm going to discuss today is I'm going to add a little bit to that. And so, we know from this earlier work about the seasonal variability of effective heat capacity over the Arctic, but what about the latitudinal variability of effective heat capacity? So that's what I'm going to discuss today, and really just focus in an annual mean sense. How does the effective heat capacity of the Arctic compare to lower latitudes, and show you that there is a difference, and that difference is important for understanding Arctic amplification. So I don't need to, show this slide to this audience, especially after Patrick's first talk. But Arctic amplification refers to the enhancement of near surface air temperature over the Arctic relative to lower latitudes and relative to the global mean. It's common to define Arctic amplification, as the ratio of Arctic temperature change to global temperature change, or alternatively, the ratio of Arctic temperature change to tropical temperature change. And I'll use both of these definitions throughout the talk today, mainly focusing on Arctic versus tropical temperature change. So Arctic amplification, or AA, it turns out it's a really robust response of the Earth system when we kick it, when we impose an external forcing on it. Patrick showed, for example, the reconstruction of temperature change at the LGM, 20,000 years ago, and as you saw from that map that he showed, the cooling in that case was amplified in the polar regions. Most of my talk today, I'll be discussing results from climate model simulations forced with increased CO2. And of course, we see Arctic amplification in those simulations as well. This plot here, however, shows instrumental observations. So this is the GISTEMP data set showing the temperature change from 1979 through 2024. Over this particular time period, you can see that the Arctic very clearly has warmed more than the rest of the planet. In particular, it's warmed about 4 times more than the global mean over this time period. This part of the observational record also has some other interesting features which are subject of a different talk. Areas of cooling in the eastern equatorial Pacific and in the southern ocean, which climate models generally fail to capture. But today's focus is, again, really on the Arctic and Arctic amplification. So this work that I'm discussing today was really initiated and motivated by some work that a former student, Tyler Janoski, did for his PhD thesis. And so Tyler was looking at short time scales of Arctic amplification in CMIP-5 generation climate models forced with an abrupt quadrupling of CO2. And so this plot on the left is from a paper we had back in 2020 that analyzed 21 CMIP-5 models in this abrupt 4 times CO2 scenario. And we showed, and so I should say in the plot, so the plot is the multi-model mean of these 21 models, showing time series for the first 30 months following 4 times CO2 of the Arctic temperature change and the global temperature change. And we found in this study that even within the first 3 months following 4 times CO2, there was a statistically significant difference between the warming in the Arctic and the global mean, so more warming in the Arctic and the global mean. Ty subsequently ran his own model simulations, again, abrupt 4 times CO2 simulations with the large ensemble configuration of the CESM. And so the plots on the right here are from his 2023 paper where he analyzed those simulations. And for this paper, Ty had actually saved out the daily data, the daily model output from these 4 times CO2 runs. And so the top plot is showing, again, the Arctic and the global mean temperature response relative to the pre-industrial control simulation. for the first 2 years following 4 times CO2. And Ty found in his analysis that even on the first day, so January 1st, following 4 times CO2, there was a statistically significant difference in the warming between the Arctic and the global mean. And I should say that, you know, when he went down, when Ty wanted to focus on these very short daily timescales, it's incredibly noisy, especially over the Arctic in wintertime. So to try to beat down that noise, he ran 100 ensemble members of these 4 times CO2 simulations, with each ensemble member starting slightly different initial conditions. And with that large sample size, he was able to show a statistically significant response even on the first day, again with more warming in the Arctic compared to the global mean. The bottom plot here is just the difference between the Arctic and the global mean temperature response, which we used in this paper as a measure of AA. So one of the implications of this result of AA developing so rapidly in these simulations is that there's been a tremendous amount of attention in the community, and rightfully so, on the role of sea ice loss in driving Arctic amplification. But we know that if we have AA in the first day following 4 times CO2, sea ice is not going to really change much right in the first day. So this is kind of, you know, another way of showing something that others have showed in different ways is that you can get AA without sea ice loss. Granted, this is a, you know, this relatively weak amount of warming, you know, on these very short time scales, but nonetheless, that warming is amplified over the Arctic region. So, as part of his analysis, Tyler did decomposition of the atmospheric column energy budget to try to understand the physical mechanisms that are causing this rapid AA response in his simulations. And this plot on the left shows the various terms, or at least most of the terms in the atmospheric energy budget. So these terms are the surface albedo feedback, the atmospheric heat transport response, the cloud feedback. SHU is the surface heat uptake response, so it's just the change in the net surface energy flux. P prime is the deviation of the Planck response from its global mean. Q is the water vapor feedback, and LR is the lapse rate feedback. And so this is now zooming in only on the first month following 4 times CO2, where again we were able to detect this statistically significant AA response. And as you can see pretty clearly, I think from this plot, within this first month, the most important contributor to the difference between the Arctic and the global temperature response is the surface heat uptake response. And so the way to think about that is that on these time scales, there's an increase in the net energy flux into the surface, both in the Arctic and in the global mean, but that increase is larger in the global mean than in the Arctic. So when you look at the difference here, it shows up as a warming contribution that's enhanced in the Arctic compared to the global mean. And so you could ask the question, well, what causes this difference in the surface heat uptake response between the Arctic and the global mean? And so, you know, to try to get at that, you have to think about, okay, well, you know, we know that there are latitudinal gradients in the forcing and the feedback, so there are going to be differences to some degree in the downward energy fluxes at the surface. But also, you know, the surface heat uptake response is the net surface energy flux response, so it's going to depend also to what extent the surface temperature has responded to that imposed forcing. And so you could ask the question, to what degree these surface heat uptake differences between the Arctic and the global mean are indicative of differences in the effective heat capacity between the Arctic and lower latitudes. And you know what the title of my talk is, so, you know, of course the answer to this question is yes, to some extent. These differences are indicative of differences in the effective heat capacity. So Ty's analysis here again focused on just the atmospheric column energy budget. So as is traditionally done, we neglected the heat capacity of the atmosphere because it's pretty small, but since we're actually interested in heat capacity here, I'm going to, for the rest of this talk, write the energy budget in a different form. And so this is going to be the energy budget of the entire column, so the ocean atmosphere column, in other words, the TOA energy budget. And so we can write that as shown in equation 1, where CF is going to be our effective heat capacity. dt is the time rate of change of the surface air temperature response, and Q net is the net heat uptake of the column. And so we computed Q net in this study as, in the results that will follow, as the sum of the vertically integrated ocean heat content change, and we've also accounted for the energy that goes into melting sea ice, because that can be non-negligible in the Arctic. So, in other words, we have again neglected the atmosphere heat capacity and the heat capacity of the land as well. We can decompose Q net as shown in equations 2 and 3. In equation 2, delta R is the top of atmosphere radiation change, and delta AHT and delta OHT are the changes in the heat transport convergence by the atmosphere and ocean circulations. We can further decompose the top of atmosphere radiation response as shown in equation 3. This is just the traditional way of doing it, into a CO2 effective radiative forcing and various feedbacks. Just a couple of other details here. So again, we neglected the heat capacity of the atmosphere, so that allows us to compute delta AHT. It's just the difference between the TOA and surface energy fluxes. We computed all of the feedbacks in equation 3 with the exception of the cloud feedback using the radiative kernel method, employing CAM5 radiative kernels from Angie Pendergrass. And so once we've computed, and I'll talk in a minute about how we get the CO2 effective radiative forcing, but once we have all these other terms, we can compute delta R cloud, the cloud feedback, as a residual in equation 3. And once we have delta R and the other terms in equation 2, we compute delta OHT as the residual in equation 2. So the climate model simulations that I'll show in the next several slides are again the same abrupt 4 times CO2 experiment, this time from 18 coupled climate models, 5 CMIP5 and 13 CMIP6. We compute climate responses as the difference between the abrupt 4 times CO2 simulation and the 30-year climatology of the pre-industrial control simulation. And as is traditionally done, we use fixed SST simulations to compute the 4 times CO2 effective radiative forcing. So here's some results. This first figure here is showing time series for the entire 150-year 4 times CO2 simulation of a few different quantities. Panel A is the surface air temperature response. And in each panel, I'm showing Arctic versus tropics. So Arctic is defined in these plots as 60 to 90 north, and tropics is 30 south to 30 north. So panel A, again, is the surface air temperature response. Panel B is Q net, the net heat uptake of the column. And panel C is the time rate of change of panel A, of the surface air temperature response. So in the slides that follow, in this study, we really focused primarily on the first decade of the model simulation. So this is the period, as you can see in panel A, where the warming is most rapid in both the Arctic and the tropics. And so the results that I'll show that follow the slide are just for the first decade of these simulations. So over this first decade, as indicated here, we found that the Arctic Q net is about 50% larger than the tropical Q net. So in other words, the Arctic climate system is being heated more than the tropical climate system. And the reason for that is just stronger positive feedbacks essentially over the Arctic compared to the tropics. And so if we go back to just a couple slides to equation 1, if Q net is about 50% larger over the Arctic than the tropics, as we found, if the heat capacity of the Arctic and the tropics was the same, then we would also expect dt to be about 50% larger over the Arctic than the tropics. But as you can see here, it turns out that that's not the case. In fact, the warming rate dt over the Arctic is actually about 150% larger than the tropics. And so what that implies is a lower heat capacity, a lower effective heat capacity of the Arctic compared to the tropics. Panel B here, the time series of Q net, actually provides some sense in another way of the lower heat capacity of the Arctic compared to the tropics. And so you see in panel B that after this first decade or so, Q net of the Arctic falls below Q net of the tropics and remains there for the rest of the simulations. And it turns out that, so these are multi-model means, but in a handful of the individual CMET models, QNet actually returns to 0 over the Arctic a few decades after 4 times CO2. So that's an indication, that removal of that net heat uptake, that the system is returned to equilibrium. We know the lower heat capacity systems return faster to equilibrium than higher heat capacity systems. So that's another indication of the lower heat capacity of the Arctic compared to the tropics. So we actually quantified the effective heat capacity CF just as the ratio of QNet to dT/dt. This is again averaged over the first decade of the simulations. And we see, CF is the rightmost column here, that over the Arctic, and there's some variation depending on how you define the Arctic, 60 to 90 versus 70 to 90 north, but they're pretty similar. The heat capacity for the Arctic is about 5 watts per meter squared per Kelvin years, and that's significantly lower than the heat capacity for the tropics, which is about 8 watts per meter squared per Kelvin years. One thing we thought was interesting when we computed these values, so I'm showing the global mean on the last row here, that the global mean is actually a little bit larger. The heat capacity for the global mean is actually a little bit larger than for the tropics. And the reason that is that there are regions outside of the tropics, in particular the Southern Ocean, where heat uptake is very large that go into the global mean and result in the heat capacity for the global mean actually being a little bit larger than the tropics. But both the tropics and the global mean, as you can see here, for both, the heat capacity is significantly higher than it is for the Arctic. And so the next question you might ask, well, why is that the case? Why does the Arctic have a lower heat capacity than the tropics and the global mean? And so to give away the answer right away, we think that that's the case because of the presence of sea ice over the Arctic. And so this plot hopefully helps to illustrate that. This is the multi-model mean effective heat capacity over the Arctic. The blue, the cyan contour here is the sea ice edge, defined as 15% sea ice concentration. And you can see here that, generally speaking, the effective heat capacity is much smaller over the ice-covered ocean than it is over the open ocean to the south of the sea ice edge. And the way that we've been thinking about this is that when you have sea ice present, sea ice is known to be an effective barrier that insulates the ocean from the atmosphere, that limits ocean heat uptake and results in this smaller value of the generally smaller values of effective heat capacity over ice-covered ocean compared to open ocean. And so and the implication of that, or an implication of that, is that when you increase CO2, these ice-covered ocean areas behave more like land than open ocean, and they warm up faster than the open ocean areas to the south. How am I doing on time?
You have another 10 minutes.
A little over 10? Okay. So I would say that the primary result from this study is that these differences in effective heat capacity between the Arctic and lower latitudes are important for understanding this rapid development of Arctic amplification that we see in the 4 times CO2 simulations. When you increase CO2, the Arctic just warm, obviously there's differences in QNet as I showed, so there's differences in the net heating, but those differences alone can't explain the Arctic amplification that we see, this rapid AA response that we see in these simulations. And you can only fully understand that response by accounting for these differences in effective heat capacity. So that, again, I think that's the main result of this study, but another, important result that we found, another interesting result that we found is when we actually try to identify the contributions to Arctic amplification in our simulations. Patrick talked a little bit about this in his talk. So this is the traditional feedback analysis that people do. So panel A, I'll start with that. I should say again, these are averages, again, over the first decade of the model simulations. And so the way that people traditionally have done this is illustrated in panel A on the left. And so you essentially decompose QNet into CO2 forcing and the various feedbacks. And if you're trying to understand which of these factors are contributing to Arctic amplification, you could do something like compare the values of these feedbacks over the Arctic versus the tropics, and if a given forcing or feedback is larger over the Arctic compared to the tropics, or in other words, it's above the 1-to-1 line in this plot, it's viewed as contributing to Arctic amplification, whereas if it's below the 1-to-1 line, it's viewed as contributing to tropical amplification. And so this plot here on panel A reveals some, known contributors to Arctic amplification. So the red dot here in this case is the surface albedo feedback, and the green dot is the lapse rate feedback. These are the two largest contributors to Arctic amplification. Other terms, notably the CO2 forcing, and we used a couple different definitions of the CO2 effective radiative forcing. I won't go into that. You can ask me questions afterwards if you want, but it doesn't really qualitatively affect our results. But in the traditional way of looking at this, the CO2 forcing is viewed as opposing Arctic amplification because that forcing is larger over the tropics than over the Arctic. Other terms that oppose AA are the cloud feedback in this case and the water vapor feedback. The Planck feedback, I think there's a little bit of a nuance there I won't mention now in the interest of time, but we can talk about that afterwards as well if you want. So that's the traditional way of doing it. And I would say that the traditional way is perfectly fine if you want to understand, the long-term equilibrium or quasi-equilibrium response, because in that case, differences in effective heat capacity don't matter, and really all that matters really is the difference in Q net between the Arctic and tropics. But if instead you're trying to understand the transient warming response and the difference between the Arctic and the tropics, in that case, that depends not only on Q net, but also in these differences in effective heat capacity that I've been describing. So panel B here on the right, instead of decomposing Q net, we decompose the warming rate, dt over this first decade of the model simulations. And the way that we get from panel A to panel B is just take each of these terms in panel A and divide by the respective effective heat capacities of the Arctic and the tropics. And when you do this, you see that for most of these terms, qualitatively, it doesn't really matter. The points move a little bit in relation to the 1-to-1 line, but they don't actually go from one side of the 1-to-1 line to the other. The exception to that is the CO2 forcing, which actually, in this alternative framework, panel B, the CO2 forcing actually lies above the 1-to-1 line. And so you can think about that as the CO2 effective radiative forcing, as I've already pointed out, is larger in watts per meter squared over the tropics than the Arctic, but it drives faster warming in the Arctic because of the Arctic's lower effective heat capacity. So this work that I've just described very recently, within the last few weeks, has appeared in GRL. So we had, during the course of our reviews, we had one comment from a reviewer that I just wanted to highlight here. And so they said, my major ask is that the authors provide more clarification regarding how much we can really learn about the observed evolution of AA by hitting the system with an unrealistic sledgehammer, an abrupt 4 times increase in carbon dioxide. And so my response to this in the reviews was kind of very, hand wavy, and I said, just because the forcing is unrealistic doesn't mean we can't learn something about the real world from it. But in preparation for this talk that I'm giving today, I started to think, okay, well, okay, that's, even though the comment kind of annoyed me at the time, it was like, I see the point that they're trying to make. These are obviously very idealized model simulations. Can we say something about is this important for the real world? So for this talk, this stuff does not appear in the paper that I'm about to present, but for this talk, I did some preliminary analysis of observations. So I focused on the 25-year period, March 2000 through February 2025, so the first 25 years of the series record, essentially. But this is also the period when Argo data come online, so that allows us to better constrain the ocean heat uptake. I used GISS temp for surface temperature. And as in the modeling study that I just discussed, I again compute Q net as the vertically integrated ocean heat content change plus sea ice volume loss. So here's some results. Panel A here is the surface temperature response, again, Arctic versus tropics. Panel B is Q net, Arctic versus tropics. And if we just consider, in this case, the 25-year average Q net, we find that it's about 0.7 for the tropics using these data sets, and 0.52 for the Arctic. So this is basically the present day energy balance in the tropical and Arctic climate system based on these data. And so despite, in this case, QNet is actually larger, than in the tropics than the Arctic. Yet the Arctic warms, somewhere between 2.6 and 2.9 times faster than the tropics, and that difference is just you get somewhat of a difference depending on whether you just take the 25-year average dt versus compute a linear trend. So there's some difference there, but it's roughly 2.5 to 3 times greater warming in the Arctic than the tropics. And so again, this implies a lower Arctic effective heat capacity. And so based on these observations, we find that that CF for the Arctic is about just under 6 watts per meter squared per Kelvin years, and for the tropics is about 20, and for the global mean about 27. So how do these values compare to the previous model results that I showed? And so this is the last column from that table that I showed earlier, and you see that in each case for each region, there's been some increase in the effective heat capacity. And we expect that. The model results that I showed here are just the first decade after 4 times CO2. So in that case, the heat capacities that you're seeing here based on the model results are really reflecting heat capacity of the ocean mix layer, because that's really where the heat uptake is occurring over the first decade following 4 times CO2. This observational analysis is a longer time period, 25 years, and the forcing wasn't just turned on at year 0. Obviously we know we've been increasing CO2 for much longer than that. So we expect that, and we know from observations that there's been some uptake of heat by the deep ocean. So we expect some increase in CF compared to the model results. But you notice for the Arctic, it's really not much of an increase. The value based on observations is only slightly larger than the model results, whereas for the tropics and the global mean, it's increased by more than a factor of 2. And so why is that? Well, that's not something I've had a chance to really look at into deeply yet, but I want to propose an idea anyway, and that is that, so this is the time series of annual minimum Arctic sea ice extent for the satellite era. And so there's been this publicized decline over the satellite era of in Arctic sea ice, but notice, over the last couple of decades, and there's some papers about this, my colleague Lorenzo Pavani has a paper coming out about this, and I know others are looking at this too. Over the last couple of decades, there really hasn't been, or at least the rate of sea ice decline has substantially slowed. And so if you've bought my argument that I've tried to make that the reason the Arctic has a lower effective heat capacity is because of the presence of sea ice, if sea ice hasn't been melting in the last couple of decades that much, then perhaps that's acted to keep the Arctic in this low effective heat capacity regime, if you will, and kind of minimize the increase in the effective heat capacity that might otherwise have occurred over the Arctic, and as a result, increase that difference in the effective heat capacity between the Arctic and tropics. So is that 3 minutes till the end of my speaking, or is that okay?
One more slide.
I only have one more, so I'll just say that. So I actually am now, in retrospect, grateful for that reviewer comment, because I think maybe something interesting can come out of this, and I have a chance to look into this more. And I'll just say that before I get to my conclusion slide, I think that this last couple of decades that I focused on in this preliminary analysis that I showed at the end here is kind of an interesting case study, because again, we've had this slowing in the rate of sea ice decline over the Arctic, yet the Arctic warming has continued very clearly. And so it's a case where there hasn't been much sea ice loss, at least sea ice extent loss, in the last couple of decades, and yet there's still been Arctic warming over that period. So implying that other mechanisms are also have been important over the last couple of decades in driving the Arctic warming. And so since I think I've said most of this already, so I think I will just maybe just make one comment on something I didn't mention. So this result that if you're trying to understand the transient differences in the transient rate of warming between the Arctic and the tropics, which depend not only on QNet but also differences in effective heat capacity, an implication of that, as I said, is that the CO2 radiative forcing alone produces Arctic amplification. But I'll just note that if you just considering the CO2 effect alone, you just get very weak AA. So I don't mean to imply that these other processes that we've been discussing aren't important. In order to get the full magnitude of AA, you need to account for these other feedbacks and energy transport changes that act to preferentially warm the Arctic. And so I think that is all I have. Thanks very much.
Thanks a lot, Michael. We have time for questions. Yes, Nicole.
Hi, Mike. Thank you. Oh, is this on? Hi, Mike. Thank you. That was very interesting. I have questions about what do you think the limits are of calculating the effective heat capacity in terms of this ratio? I could imagine when the warming rate goes to 0, it's poorly defined. So just how do you figure out how far you can take that? Related to that question, I know you're looking at the annual average. I could imagine in summer this being particularly difficult, but have you looked at winter, for instance?
Okay, so I'll answer the second question first because that's the easier one, I guess. So for this study, mainly the results that I showed today were obviously only annual means. I have limited, to a limited extent, looked at seasonal data, but it's been mostly this work has been focused on annual means. Your first question, though, yeah, there was a lot of messiness that happened before I came up with something that was actually publishable, for the study. And so that issue, like that you pointed out, it becomes very problematic when you're computing the effective heat capacity as the ratio of just Q net to dt, because especially if the warming rate is not large, like you said, you have times where dt is near 0, and so the problem is ill-posed. So that's one reason why we mainly focused on the first decade of the 4-time CO2 simulations, because we have a large warming rate over that period. And also why I was able to really get away with looking at the observations for the last 25 years, because there's been a very clear warming over that period. But yeah, you're right that, so my co-author on this study, Lorenzo, said, well, why don't you create a plot of CF for the entire 150 years of the 4-time CO2 simulation? And I said, well, I thought about that, but when you actually go further past the first decade, the warming rate goes to 0 in both the Arctic and tropics. So trying to define CF in that way, that's problematic. There have been other studies that have quantified CF, and they've done polynomial fits to model output and such to try to estimate CF. And I played around with, try to mimic that to some degree, and try to various other approaches to estimate CF. And in the end, I wasn't able to get anything that was really satisfactory, and so I went with this approach, which at least, I was able to convince myself was reasonable, because it's just based on the energy balance equation, and it's computing, just CF as the ratio of those other two terms, and but yeah, there are limitations to it. You can't. There are cases where that approach doesn't work, as I found out.
Thank you. Till, you had a question? Same question. Okay. Perfect. Other questions? Yes, Alex.
So you mentioned in the Southern Ocean, it's much higher, the effective heat capacity. There's sea ice in the Southern Ocean.
Well, I'm not referring to the sea ice covered part of this. I'm referring to, north of the sea ice edge, yeah.
Okay.
Yeah.
So then how does that look when you break it out, like in terms of what's going on in the non-sea ice covered part that's making it so much higher?
I mean, I think that just so maybe I'll go back to, this is something I didn't point out because I was worried about running out of time, but why is it not going back now? Okay. Now it goes. I think there's some, I have one plot here that tends to, it takes a few seconds to load, and then it slows up everything else. Okay, so here's where I wanted to get to. And so I think just generally, I mean, generally speaking, you have maxima in CF where the mixed layer is deep, where you have, water sinking. And so you see that in this plot for the Arctic. These are areas, I think, of deep water formation in the models where you have these CF maxima. And so in the Southern Ocean, we know that's one of the main regions where deep water forms and where you have sinking of water masses. And so I think that's, I think that's, in a general sense, like what's going on, why you have the larger heat capacities in the Southern Ocean, just because you have this exchange of surface and deep water. You have deep mixed layers driven by the Southern Hemisphere westerly winds. And so I think that's just, again, generally speaking, why the CF is largest in the Southern Ocean.
And then a related question is to what extent this is state dependent. I mean, you kind of implied that in the Arctic, because of the slowdown in sea ice decline in the last decade, that this could be changing the contrast.
Yeah, I think it's yeah. I mean, if this argument is correct that I've tried to present here, then it very much is state dependent, right? And so I think that there's been some studies that have looked at like transient CO2 runs where CO2 is increased, or just greenhouse gases more generally. Some of these future scenarios, like, and looked at how the evolution of AA changes over long time scales, like multi-decadal to centennial time scales, and have shown that when sea ice goes away, AA becomes much weaker. And so, and the attribution of that has been, because when that happens, you lose these important sea ice related feedbacks like the surface albedo feedback, the insulation feedback, and so forth. And I think that's true, but I think an implication of this study is that potentially the increase in the Arctic effective heat capacity that happens when you lose the sea ice is also a reason why you get slower rates of Arctic warming. And so I think that's, but yes, so that's an example of state dependence, and I think it very much is a state dependent problem.
Yes, Patrick.
So I had a question about the Antarctic, but maybe you can expand upon it, but I'll ask that. So let me ask, go back to one of your early plots where you showed the abrupt 4 times CO2 and the time series where you had like the months. Yeah, so I saw there, so it increases and it decreases, it kind of goes away for, between month 7. So can you talk about that wavy structure, why it's like that?
Yeah, so yeah, thanks for asking that, because again, a detail that I did not go into because I was worried about my time. But yeah, so this is just, these are just, I don't think I said that when Tyler ran these 100 ensemble members of the 4 times CO2, obviously that's a large number of simulations, so he just ran short 2-year simulations, and so we're showing just the 2 years of his simulations here. And I mean, I think that this is really just reflecting, the known seasonality of Arctic warming in AA. So, you see that the minimum difference between the Arctic and the global warming happens in the summer months, and it's known that that's when AA is at its weakest, and the maximum happens in the fall and the winter, as you obviously know well, as you talked about in your talk, and that's related to the sea ice loss and the increased ocean to atmosphere heat exchange. So I think we're just seeing the well-known seasonal
evolution of effective heat capacity, because you're losing sea ice and you're reducing the heat capacity in the summertime.
Yes.
You have less sea ice, and then in winter you have.
Yeah, no. So I mean, I think that you're seeing some manifestation of the seasonal variability in CF here, the effective heat capacity, but also the seasonal evolution of these sea ice related feedbacks that are known to be responsible for this seasonal cycle.
So that's kind of what I thought. So I was curious then, as a follow-on, what happens if you start these simulations in a different month? Because it looks like you started them in January. When
Yes.
You started in July. And
Yes. Well, yeah. So I did not show this, but yeah, in the paper, Ty had done simulations where he imposes 4 times CO2 on July 1st instead of January 1st, and yeah, so you still get Arctic amplification happen on relatively short time scales. It's not day 1 following 4 times CO2. You need to average like the first few weeks, I should say, after 4 times CO2. But you do get, it's weaker, it's a weaker signal, but you do get it even for initializing in July. Yeah.
Just a very quick one. You said that the sea ice CEFF is similar to land. Just out of curiosity, have you looked at what the actual CEF would be over land and how that would compare?
I have not, no. Yeah, so we kind of did maybe the lazy thing and just said we're going to ignore the land heat capacity for this. But yeah, I think it would be good going forward to try to actually quantify that, yeah, but I have not looked at that, no.
I had a question about just framing the results. It seems like what you're explaining here is the transient response. It's the rates of warming in the Arctic being greater than the rest of the globe. But when it comes, so there's a transient problem, which is also, that's of huge interest, right? But then there's the equilibrated problem. And I'm wondering if you're seeing this as a mechanism for understanding, the adjusted response to, say, 4 times CO2 or doubled CO2. You might imagine ways that could be the case, but I'm wondering if that's what you're thinking about, or are you thinking more about the transient response to radiative forcing?
No, I mean, I'm thinking about it in terms of the transient response. I don't see, as I think I pointed out earlier, I think for the equilibrium response, really, we just need to know, it doesn't like me advancing, I guess, too fast. No, but I think for the equilibrium response, we just need to know, these guys basically, panel A, so QNet, how the forcing and the different feedbacks are different between the Arctic and the tropics. Because given enough time, the system is going to respond, to those posed energy perturbations. And so, I think the heat capacity differences are really relevant for understanding the transient warming rate.
Yeah, one, I haven't thought enough about it, but I'm thinking that there might be like a rectified effect of a seasonally varying heat capacity with a seasonally varying response, and that there might be something, in something nonlinear going on that might, because often a fully adjusted response might look really different from, with all those nonlinear effects coming in. But anyway, obviously.
Yeah, no, I hadn't yet, but I hadn't thought about that. But yeah, I think that's something that's worth thinking about. Yeah, thanks.
Thank you. Yeah, we have time for one more question. Reggie.
Hi. Hopefully this question makes sense. In the results that you showed, it seems like the presence of sea ice for at least part of the year is really what is driving these differences in heat and how creating the Arctic amplification and allowing the Arctic to sort of move not in concert with the rest of the globe. And I was wondering, because it seems like already in in your model in like the summer months, there's very little different. They do seem to already be moving almost perfectly in concert, and it's really just during the winter months where you have the presence of the sea ice that we're seeing a difference in that heat capacity. And so, I guess one is how do you think about sort of when people talk about ice-free dates where like, you have 0 ice in the summer months, does that really matter as much as maybe it matters in terms of the quality of the ice, the albedo of the ice, but how much does that matter in terms of the ice that does develop in the winter and the effect that has? And then is there some insight from this into whether it's the quantity of sea ice that is really allowing this effect to occur, or if it's the specific location within the Arctic of sea ice that is changing the movement of energy through the system?
Yeah, that's trying to think which part of that do I want to try to address first. I think that in terms of what is the property or properties of sea ice that matter, I think extent is probably my thought is the most important. Just limiting that ocean atmosphere heat exchange. In terms of whether there are particular regions where the sea ice cover would be more important than others. Yeah, I don't know. Maybe, I suspect it would be more important if, in regions where the mixed layer is climatologically deeper, and, regions where that can have deep water formation, for example, like the Labrador Sea, if there's sea ice cover in the Labrador Sea, maybe certain regions like that it would be more important. But, this is not, I haven't looked, more regionally within the Arctic to try to understand, where it would be most important. Yeah. What were other parts of your question? Sorry,
Yeah, thank you. That makes sense. Yeah, the other part was about the summer ice-free months, and I guess just getting to this, to maybe the more specific thought was, well, if there is still ice in the summer, at the beginning, certainly I would expect at the very beginning of your model, there's still summer ice that's there, but it's having but the Arctic and tropics are moving in concert with each other during those months, then how much does that ice actually matter? And is it because there's not enough of it, because it's not in these key areas?
yeah.
Does an ice-free year actually, from this perspective, make like a significant critical difference?
Yeah, so I think you're right. I mean, I think, so if you look at this plot here, yeah, like in the summertime, like you said, there's really not much of a difference between the Arctic and the global mean, and I think that just the melt back of the sea ice in the Arctic over the summertime is significant enough already that you expose enough additional open water that it increases the effective heat capacity enough that it really minimizes this difference between the Arctic and the lower latitudes. And so from that perspective, I don't know how much whether a change, like when the first ice-free Arctic day would happen, how much of, an additional effect that would have. I would suspect it's probably pretty small, just based on, just compared to the present-day seasonal cycle. I think the present-day seasonal cycle is large enough to really have a substantial effect on the effective heat capacity again, and really make the Arctic behave, thermally more like the lower latitudes. And how much, and the additional effect of further ice loss, at least from the perspective of, when the first ice-free day would happen. I'm not sure how much of an additional effect that would have, whether that would be detectable. I'm not sure if that's answering your question or not. But.
I suggest we continue this discussion over the coffee break. I know people had been asking about coffee even before we started, so now it has finally arrived. You can go just over here outside, and we'll meet again here. We'll start at 11 sharp. Thank you all, and thanks, Michael, again.